it's going to be, well, mix of lecture and research. It's going to be a little bit loose. I think we're just going to end with a little bit kind of forward-looking kind of things, looking into sensing. I actually probably will go back to some of the things that you brought up in the first application discussion. So what I'm hoping that we'll get from like this very final lecture is I'll talk a little bit about, can we try to identify the underlying principles behind quantum advantage in network sensing? What are the different types of advantage you can hope for? And also, be able to use that to discuss a bit and evaluate the possible applications of network quantum sensing. So it kind of goes a little bit back to also when we had the application discussion earlier, that one can say network sensing, but what exactly do you really mean by that? Where does the quantum advantage come from? Is it really something that pays off, given the arguably quite high cost of making network quantum sensing? All right, then let me just switch here and go to that one. We don't want to do this, I think. You already did a lot of groups, so you're off the hook. And it kind of, we discussed it nicely in the first one. So let's just continue there. I've tried to kind of group this into 4 different areas. I might be overlooking something. Maybe it's not the best title for these, but one is kind of Heisenberg versus standard quantum limit. So this is a bit, the idea here is that, well, okay, we have a collection of sensors, and they can sense their signals on their own. If we entangle them together, can we have a higher sensitivity? Can our signal-to-noise scale as, the number of sensors instead of square root of the number of sensors? That is this kind of Heisenberg versus SQL. That's, I think, the most kind of the oldest thing from quantum network sensing. That's where you have like this network of clocks and whatnot. Then there's something like loss across signal combination. So quantum telescope arrays, for example, would fall into this. So it's not so much about combining sensing signals. It's more about actually just circumventing transmission loss, kind of like a repeater. Quantum processing assisted sensors. So this is where we say the network is more a network between your sensors or your signal and your quantum computer. What would the quantum advantage you can hope for there? It's an example of that. And then finally going back to more fundamental things. Okay, if we have quantum networks, what kind of fundamental sets can you do? Do we have access to some interesting quantum mechanical non-local measurements we can do, and how can that help us with these things? So these are kind of the 4 examples I can think of for quantum network sensing. And we'll just basically go briefly through them. I'm not going to be super detailed. We're not going to derive stuff. It's going to be a little bit of a hopefully relaxing lecture for you guys. That will more be, sit back and relax, chat in the discussion. You won't be called upon to go to the whiteboard and derive stuff. Okay, so first this one. I think the general setting here is that you have a number of sensors here depicted these nodes here, and they're each sensing some parameter. Here just called phi 1, 2, 3, 4, and up to phi 6. And I think the question you're asking is, okay, given a restricted number of probes or sensors, does entanglement give you an advantage, right? And the answer is not always. You need to really carefully specify, well, what do you mean by restricted number of probes? Is it such that, within each of these sensors, it's just an average number of probes that I'm restricting, or is it a strict limit? Atomic clocks, a good example. There you might say, well, it's really like I cannot fit more atoms inside my clock. That's a strict limit. If it's something where you say, well, I'm doing coherent state kind of things, it's an average thing. That's different from whether it's a discrete number of photons, for example, that you can have. And that matters for whether you will get advantages when you combine these signals or not, actually. I think a more easy evaluatable thing is, do you care about the individual signals, or do you care about some global function of them? Right, so if do I care about estimating each of these phis because I want to learn all of them? Or do I just want to learn something about a general property of them, the average, for example? And I think a good rule of thumb is, if you do not care about some global information, but read about each of them individually, you don't win from entangling these together. So in many cases, at least as shown for linear functions of these, if you care about really, I want to estimate each of these phases, not just some linear combination of them, something like that, you don't win from entangling together. Right, so what we should find an application of this, it should really be an application where it's a distributed sensor, and somehow what we're trying to estimate is a function of the individual inputs. Otherwise, I don't think you can be very hopeful of getting something. And also, well, okay, so what is that we actually gain? Now we're estimating this function of them maybe more efficiently. And this goes back to the number of probes, but if I locally can make very precise measurements, then I don't need to go to this entangling thing, right? And then a way to estimate a function is that I estimate each of them individually, and then I calculate the function. If I can estimate each of them individually good enough, because I have local access to many probes, I mean, it's not an issue, why would I ever entangle them? So it would only be in a situation where locally, well, you are, okay, now it doesn't work, I think, but see. It should really be a case where, yeah, you're locally restricted, and where you care about a global function. And that immediately limits a little bit, where would you apply this? Right? I mean, what kind of field do we know of that we want to sense in a distributed fashion, and we are limited probes and whatnot? It starts to become a bit difficult to find the applications for this. One example that always is brought up, because it's one of the first things, was like this network of clocks, where we say, okay, we know that atomic clocks, you might have a strict limitation for how many atoms you could fit in, right? The sensitivity of that clock, the Allen deviation of that clock, it basically how fast it averages down. You can, that's set by the number of atoms that you have in your clock, basically. And if you entangle those atoms together, you can go from, in principle, standard quantum limit, where it goes down a square root of the number of atoms, to 1 over the number of atoms. Now, network of clocks is kind of like just extending that to now I have separate clocks. So if I have separate clocks, I can again measure each of them individually and then average those together to get an even better clock. But just as we would do locally, if I now just make a insect entangled state to involve all these atoms, then I can in principle average down faster. Note, however, what do I gain? It's a factor of square root of n. N not being the number of atoms here, the network thing just gives me the square root of the number of clocks that I'm doing. Right? So if I'm doing 2 clocks, you get a square root of 2. So you need to really have a large network of clocks to gain significantly from this. And it's nice, right? I mean, it's something where we do fulfill the fact that, okay, we want to care about a global thing, we care about the average of these things, so we could gain something, yes. We have something where we have a limited number of probes, that's also true. Then it becomes more on the practicality kind of, in what setting do we have a lot of local clocks that we want to put together. So challenges, of course, are also, when going back to what we discussed this morning, is it feasible? How much will it cost? Okay, locally in a lab, maybe actually that's where you will see it first, right? Okay, I can pitch this many atoms into my trap. I need to build another trap next to it. Maybe I can entangle to get even better. But any loss of defacing of your entangled state, that will limit how much you gain, right? So if you have loss of defacing, instead of having a scaling advantage, you end up with a constant factor advantage. It'll scale down a standard quantum limit, but it will have a factor in front, basically. And again, what we're talking about here is that it's how fast you average down in your Allen deviation of your clock. So I can get the same sensitivity or the same Allen deviation by averaging for a longer time without entanglement. So it should be an application where I care about a very fast signal, very precise fast signal. So again, kind of finally, like when you think about, okay, does quantum sensing help? We should really keep these things in mind to see, well, in the end, does it matter or doesn't it matter? What are actually the applications you want to do this for? And outside of clocks, yeah, it becomes difficult to, what are the fields that you actually want to sense, where you want to care about global local properties. I don't know if there are anyone that has any ideas outside of clocks. Yeah. Sorry? True, yes. You want something, yeah, for GPS, something that is moving or something like that, you might want fast time. Yes, I agree. That could be a case of this. Yeah. No, I agree. Then the question that naturally follows up is you know, can I do this with just entangling a local atomic clock? Do I really need to do a network of clocks to do it? I mean, it becomes a question of what are actually the requirements from the satellite, right? I mean, right now we're not doing even entangled clocks. We're just doing non-entangled clocks. And just entangling locally the clock, I guess, could give you advantages. Then if you assume that first, then the gain that you get from square root of factor of 2 or 3 or 4 from entangling clocks together, is that worth it? I don't know. I think it's also something to apply, for example, we discussed in the morning, which is just interesting things to think about. So I'm not ruling it out or anything like that. But for example, these things will distribute things for detecting earthquakes, for example, or something like this. But we need to think carefully about what is it that we're trying to detect? Is it a global feature of these things? In that case, then yeah, maybe there's something. Honestly, I don't know. I don't know how you really detect earthquakes and predict them and whatnot. And I guess many of us don't. So it also points to the fact that in these applications, it's very, very good to go out and talk to people that actually do these things and figure out exactly what the signal that is they're doing before we as quantum physicists say, well, maybe you can use it for that. And indeed, maybe you can, but determining whether it actually gains you anything, you kind of need to really carefully look into these kind of things for what you need to do. All right, that was the first one. Let's go to the second one, which was also mentioned this morning. So this was about telescope arrays, right? And just to clarify, so where is it that we're talking about this? Well, it's particular for optical telescope arrays. The reason is the following. It really matters what the brightness of your target is. And in optical optical machine, normally you have very faint signals, and that's where you can hope to get some kind of quantum advantage. If you have a strong signal, which is the case for radio waves, for example, most sources, you don't gain anything. The reason being that for strong signals, you just do local heterodyne or homodyne measurements. Basically, you just record the amplitude of the field that comes in, classically, and then you just compare it classically to get the relative distance between them. And this works perfectly fine when you have a strong signal. When you have a weak signal, there's a fundamental difference in, I think it was mentioned also this morning, quantum phase information, meaning how much information can you extract about the relative phase, for example, between these telescopes, between whether you do local measurements or whether you do non-local measurements. The key point here is, however, non-local measurement doesn't necessarily mean that I need to share entanglement between these things. I can just take the signal, send it to a local beam splitter, interfere them, and detect it. The reason why you get this fundamental scaling difference is the fact that when I do that, I only get a measurement result when I actually have a signal, right? When a photon comes in, that's when I'm going to click my detectors, and I get a clear measurement of the signal itself. When I do the local measurement, there I basically also measure when there's vacuum, right? Because I'm mixing with a strong local oscillator, and then I'm measuring basically the outcomes come out there. So whether there's an input or whether there's not, I'm still going to measure and get results. I can discriminate my signal from the vacuum noise, and that is what leads to kind of this fundamental difference between these two. Another point of caution, it matters what kind of source you're looking at. This is true for thermal states. Thermal states is basically what you would expect to receive from a star. That's why it's for astronomy. Other sources, you don't gain. Let's say it's a coherent state that is split between two. There's no difference between these two. So it matters what type of signal you're looking at. Thermal states, okay, that's actually good. That is what we expect to get from SARS. There you can have this difference. If it is a weak source, if it's a strong source, there's no difference between them. You just do local. And the other thing is, you don't need quantum entanglement to do this. You can just combine them. So why do you actually care about quantum entanglement? Well, it's because you have loss in combining. So actually the quantum advantage doesn't really come from doing some weird quantum measurement. It's basically I'm just circumventing transmission loss for combining these two together. So when you have thermal light, you have your signal. So this is actually not exactly thermal light because there's coherence between vacuum. I just copied this from a paper. My apologies. In thermal light, you would not have no coherence between the vacuum part, which is 0 on left, 0 on right, and the one photon thing. And that is actually crucial. If you have coherence like this, then there's no difference between non-local and local. You can do just as well by doing local. So just a thing there. But why I copied this in is just to say that basically, assume there's no coherence here, then doing this correct direction, you get a signal-to-noise ratio that scales with square root of this mu here, but you have this transmission loss impact. So what can quantum do? Well, we know that we can teleport signals and that way circumvent the transmission loss, so we get the same scaling, but no loss, attenuation of the signal. That's the quantum advantage. So you need to also think, okay, do I want to do this with telescopes? Well, it depends. Are your telescopes in space? Maybe the transmission loss is not so bad. Are they on ground? Maybe they're what's worth. How big a baseline do you want? You know, several kilometers, yeah, then maybe indeed these losses are going to be really bad for you, right? But that's the point. Yeah, and the fundamental difference is that if you do local measurements, the SNR scales with mu instead of square root of mu, so if mu is very small, that's where you really gain. And this is also why if you have a strong source where mu is close to 1 or even above, you don't gain. It doesn't have to be just 2 telescopes. Of course, this generalizes to more, but it's just to think that that's kind of when people talk about telescopes and quantum advantage, it's actually just transmission loss. For now, I mean, there might be other applications. So, you know, the things to explore is, well, if you have a number of telescopes, for example, and one big problem, maybe I actually have that, okay, I don't have it, with these telescopes is you need adaptive optics if it's on ground because you have turbulence in the atmosphere that basically blurs out your image. So even though you have a big telescope, if you don't do adaptive optics, it just behaves as a very small telescope. The resolution is not very good. And the way you do that classically is that you estimate kind of this phase noise, you do wavefront sensing, you do adaptive mirrors to correct for it, and in that way denoise your signal. There are probably, but it's a little bit early on even in classical literature, correlations about this noise across a telescope array because, you know, atmosphere, where does this turbulence come from? It comes from wind and whatnot, and there are most likely correlations as that moves across your telescope array. So maybe there are correlations that you can explore when you do non-local measurements to better extract them, for example. That could be something, but I think that's still early on. People have not looked into it, but it could be something where you can say, okay, can we get other advantages on these telescope arrays except just the transmission loss, which is also maybe useful. But it would be nice if there's something more you can do, right? Yeah, just a little bit of advertisement. That there was actually recently a demonstration at Harvard demonstrating this kind of entanglement-based interferometry to circumvent the transmission loss. And the reason I put it on here is also the gate they used to map the photon into the spins is the amplitude-based gate that we discussed in the first lecture, right? So this is exactly what they're doing here. This is what you saw before. There's difference between reflection or transmission. They use that to take the photon that comes and teleport the state of the photon into the spin. So what it means is, going beyond telescopes here, we actually have a method to map the phase and amplitude information of a photonic wavefront, here just 2 pixels in some sense, into a qubit system. Maybe we can do more things than just, you know, circumvent loss. Maybe we can do some processing things, just the next thing here, right? Challenges I also want to mention a bit here. So when we do, for example, this entanglement-based and non-local interferometry, if your entangled state is not good, and if when you do the mapping, basically you're not doing it well enough, instead of having a scaling difference, you'll get up with a constant factor like before, still scale as mu, but start up lower. It depends on how noisy you are compared to your expected signal, basically. If your noise is greater than your expected signal, you'll get, again, the same scaling as local, but with a factor improvement. If your noise is signal, you'll get kind of that scaling factor. Yeah, and then really, adaptive optics, I mean, quantum is not solving some of the other issues that we have with long baseline. How do you do efficient adaptive optics across an optical baseline? You now need to have, basically this stable to down to optical wavelengths. Pretty demanding. But that's where maybe classically there's a need for that, but maybe there could be quantum techniques that could help for that, for example, solving another issue. All right, I'll just pause now if there are any questions on these two first things before moving on. Yep. So, about this question, first one, are you aware of the access of the small scale? Right, yeah. I think people have at least speculated that maybe these Heisenberg kind of things on local scale for molecular imaging, for example, something like that, where you say, okay, I'm sending a number of photons through a sample, and I care about, different parts of the sample. I want some kind of global thing, and limitation on probes comes from the fact that you have some photon toxicity or something like that. So you can't, you're destroying your sample if you send too many photons. That's something people thought about. I think people also thought about if you want to measure in a quantum network, I think if timing signals, I think between them, like, or phase differences, maybe there's something there. To be honest, that I don't know too much about. So I think there's, yes, people have thought about local networks on this thing here. But that's kind of the extent at which I know it. But I definitely agree that maybe that's the more natural place to look, more than the large scale for these things. Yeah. The way to understand it is really, if you have a local sensor and you entangle them together, that's the Heisenberg. If you take those sensors and say, for some reason, it's not completely local, well, then it's the same thing, right? It's just entangling together, you win. Yeah. But whether it's really a network or not just depends on what do you call a network? All right. By the way, I hope this is not meant to be a discouraging talk. It's just to be a talk about, be careful, see where the quantum advantage comes from, and I think the encouraging thing is there are questions that we have not answered about where can you get these advantages. So more take it as you go out and look for these advantages. What are the things to keep in mind? What are the guidelines you can maybe use to identify whether there's a real advantage or not? Okay, so I said, okay, we can actually, with the telescope thing, it was not just to do the non-local interferometry, it actually also showed that we could map the photonic field into a qubit register. That also opens up the question, can we use that for something, right? Can we maybe do these quantum processing assisted sensors? The main idea, you can say, is, okay, well, we know quantum computers, they're really good at handling quantum data. If you have a very weak signal that comes in, it is a quantum state. Actually, if you look at a star that's very far away, how could there be any quantum coherence? Well, it's a point source, basically. There's no coherence, it's a thermal state that comes in, but when you look at your detector array, there's going to be a very good spatial coherence across. So actually, at the single photon level, it is sort of like a pure state with a photon that could be in a superposition of hitting any kind of pixel on your detector. So that spatial coherence is also what you leverage in adaptive optics and whatnot. So this is definitely something that people agree on, that yes, you have that kind of coherence there. So we have a quantum state. We can map it, as demonstrated by this recent experiment, into qubits. And then what can we do? So currently, they don't do that, right? A signal comes in, and they detect it right away, because they don't have any way to store it. So they detect it, they measure it, they try to build, integrate information in a classical computer, and then they process it. For example, if you're looking at things like exoplanet detection or something like that, they need to build an estimate of how does your spectral noise, meaning how does the starlight, which you don't really care about, you care about the reflected light from the exoplanet, how does that look like, so I can remove it afterwards in processing. When you do that, you're combining a lot of noisy estimates. Think of it as, I'm now estimating what the wavefront looks like for each of my pixels in my detector, and I'm combining these things to now try and do some principal component analysis or whatever to extract it and remove it. And as soon as you combine many noisy estimates, if these are independent noise, right, just use standard propagation for error, what you're looking at the end, that noise will accumulate. So you end up with a more noisy estimate. So you can ask the question, well, could I circumvent that if I say, okay, I'm loading now my system in, and I'm not detecting it, so I'm not adding shot noise on top of this, I'm not estimating it. I can now integrate in time the amplitude information. I can now apply quantum algorithms to try and do these things that I want to do, and then measure, such that my measurement, I only get kind of the shot noise, the statistical noise on top of what I really care about, and not all the elements that I need to extract in. Just to say, we're kind of already doing that whenever we can. So this, in adaptive optics, for example, this is what you're doing. You're trying to, you classically estimate the wavefront, so that's where you're not doing it, but then you try to feed it to an adaptive mirror that corrects the wavefront in amplitude, right? So that adaptive mirror is not measuring what comes in, it's just applying a unitary transformation actually to your quantum state to denoise it. The reason why they're doing that is because it's more efficient than if you did it in the post-processing. Mode sourcing, where people also say, well, okay, we're going to put this into different spatial modes. So there have been some recent and semi-recent results on where you say, well, you can have super resolution of distinguishing between two point sources, for example, all sorts of caveats, but where you say, instead of measuring in a direct pixel basis, you can measure on a different kind of spatially correlated basis, and you can extract more efficiently the separation between point sources. So this is in some sense the same thing. We're saying instead of measuring in the pixel basis and then from that extract point sources, if you change the measurement basis, you can measure more efficiently. There's not so much quantum there. It's kind of like you can do this within your optics and whatnot, because it's still at the, you detect every photon, you're just updating your measurement basis. So what is it that quantum processing give you? Well, okay, one thing is, of course, adaptive optics and whatnot, this is really hardware that you're doing it with. It's you have a certain thing that you can control to implement the unitaries, so naturally you're kind of limited to what kind of unitaries you can do, and it is really like a mechanical thing if you want to change the unitary to do. In principle, such unitaries we could also implement in a quantum computer, and it's completely, programmable. We just need to do the circuit to do it. Okay, that's one thing, and it's very practical. I don't know how much you would gain from that, but in principle, yes. But the other thing I think is more interesting is we can integrate the amplitude over time, because some of these weak sources, if you now come one photon, we can store it, wait for the next photon, and interfere those together. And that allows us to, could allow us to extract more information. Just think of, for example, not that it has super practical, but think of a swap test, right? If I want to check if, so if you have a star and an exoplanet, the wavefront is going to be slightly different for the two. So let's say the simple example, let's say I don't know whether there's an exoplanet or not. Then what I can do is I receive a photon, I wait for the next, and then I do a swap test. I'm asking, are these two the same? Now the wavefront is something that is across a detector array of maybe 10 by 10 pixels. So it's like a 100-dimensional quantum state that I'm asking, is this the same as the next one? So classically we know, okay, well there I need to estimate actually what this quantum state is. I need to do tomography, right? So the sample complexity I need to do scales with the dimensionality of the problem, dimension 100. With a swap test, or basically what you're doing in the swap test is you're just interfering these directly, right? And you get a 1-bit measurement outcome of whether, are these the same or are they not? So answering the question, do I receive light from different sources or do I receive from one source, I can answer without having to estimate the wavefront, meaning that my sampling complexity don't have this penalty of some factor that scales with the dimension of the state. And I can do that because I can interfere these two together. So that's where you can hope to get some quantum advantage here, is that if you ask specific questions about the state that come in, but doesn't require you to learn the entire state, but just certain properties of the state, you could do so more efficiently with quantum things. A little side note, you can also use some of these things for classical communication, deep space communication, to basically extract classical information more efficiently. But I won't talk too much about that. So just a little bit more meat on this than the expanded example. Actually, this is what it looks like when you do it classically. Up here, that's a star and an exoplanet in the first picture. And when we say spectral noise, that's all this you see here. It's basically you put a coronagraph, which is something that blocks out part of the light. Basically, this is what is blocked out, what you call the dark zone. And you can see there's a very big difference between if you're outside the dark zone or in the dark zone in terms of how much light you receive from your star. But there will still be something left. This is what you call the spectral noise. And we're hoping to see, basically, can we find an exoplanet that is, somewhere here in this dark zone. That exoplanet might be 10 to the minus 10 weaker than the full bright light from the star. That's why you use the coronagraph. Then you can get to something like, maybe there's an order of magnitude, maybe they're kind of comparable, something like that. But you're still left with the thing, that exoplanet is somewhere in that blob. And how do I see it? So classically what you do is that you do all sorts of measurements where in the end, they rely on tomographic things. You estimate what is the spectral noise, and then you remove it in data processing and see what is left. And then hopefully you see a little blob that's left, and that's your exoplanet, right? But it requires you to learn this spectral noise first, and that scales with dimensionality. And for these, I think these are 20 by 20 pixel images, right? So you got like a 400 kind of dimension problem. You need to estimate these things around. And going back to mode sorting and stuff like that, if you know in a priori what this is, then it's fine. Then you can just design the optimal measurement basis to do it, and you don't win anything from quantum processing. The problem is, in most cases, you don't know, because this chronograph, it makes a weird kind of point-to-point function on your detector, and your telescope is not stable. It vibrates. So over time, it changes. So you need repeated tomographic reconstruction of this in order to do it. And that's why it's kind of difficult to apply these mode sorting techniques directly, because they kind of assume that you already know what this is, and then you remove it by deciding the measurement. So where quantum really can help is, let's embrace that. Okay, they don't know what it is. Now, can I now use my quantum processing to measure in the optimal basis, even though I don't know what that basis is? And you can, basically, in that way. So you don't need the classical reconstruction, and that means that you lower your sampling complexity. So one thing, just to go through what we looked at here, was you take, again, these optical signals, think about the telescope and this experiment, you store them in your qubit memory. By the way, yes, you need, if there's 100 pixels, you need 100 of these spin photon interfaces to receive it, but then you can compress the information afterwards into a logarithmic number of qubits. So for processing, even if you have like a 30 by 30 pixel array, you only need 10 qubits to process it, right? So it's not a big quantum processor that you need. Then you can use quantum principal component analysis type things, signal processing, to sort the signal into its eigenbasis, which allows for the optimal measurements to extract your exoplanet. And the nice thing is here, what this technique gives us, I'm not going into details, but basically what it gives us is that I get a guarantee that I'm measuring in the eigenbasis. I don't know what the eigenbasis is. So I just get access to, basically, these are the eigenstates. They're prepared in my quantum register, in my quantum processor, and I can sample from them. I don't know what they look like, but I can ask about their properties. So if I want to estimate an observable of an exoplanet, I can take the observable and sample in the eigenbasis, which can give me kind of the best sampling I can get without knowing what it is. So, for example, if you look at, okay, what can you gain? It can be quite substantial. It depends on exactly what the signal is, depends on what noise you have. In general, you have that classical means where you have tomography. This is if you have an n by n pixel array, so think n could be 10, for example, then it's 1,000,000 you have in front here. Now you've circumvent that factor with quantum. It's kind of interesting to see that this epsilon here, that's actually your target signal to noise. So 1 over epsilon is your target signal to noise ratio. And you see that the quantum actually scales unfavorably compared to classical with that. So if I just look at that, I would rule out, hey, there's no quantum advantage. But then look into the practical thing, they have very few photons coming from these stars, like 1 per second or something like that. They're never targeting an SNR of 10 to the minus 6. They're targeting an SNR of 10. So even though that I have, here it goes as epsilon to the cube power, here's epsilon to the second power, well, a factor of 10 compared to a factor of 1,000,000 still gains me a lot, right? That's what you end up in here. But you can still have a sizable reduction in number of samples that you need. And that means that basically, why do we care about that? Well, that's because we still need this telescope to be stable while we take the image. It's super difficult to keep it stable for months. It's much easier to keep it stable for minutes. So for example, new things that NASA want to do, like Habitable World Observatory, which is one of the things that they're working on right now, they're really struggling with stability, right? It's something like they need picometer stability across the telescope for a very long time. Extremely challenging. Anything that can reduce the signal acquisition time, even by a factor of 4, they would very much like to have. Arguably, still requires quantum processing here, right? So it's not something you can just take and deploy, but it is kind of something that to keep in mind. Another thing is that it doesn't require fault-tolerant quantum computers. So I think one of the things to think about in quantum sensing is it's not a universal quantum computer that you need. Specific things that it needs to do. Here, for example, if you put this in for like realistic settings, it's about 20 qubits that you need, and circuit depths around a couple of hundreds. So we're getting close to what we need. We actually today hardware. We might not even need fault tolerance to do it. So in some of these things, you might have a special purpose quantum computer that could lead to more near-term advantage or not. But it could go beyond astrophysics. It's the same for potentially molecular imaging and whatnot. However, yeah, so this is just like, you could do it with a silicon vacuum centers, right? Map it and put it into some of the quantum processor. There's still some challenges here. And I think, okay, one, of course, goes without saying, of course, noise in conversion and in operations, that degrades your signal, right? I mean, so you need to make careful, how much noise will I add in this? And for these things, you need noise around, maybe percent when you map it in, and you need something like 10 to the minus 3 for the operations. So we're kind of close to what we have in hardware here, but still is state of the art. But a very concerning one is that all quantum transducers are narrow band. So some of the broadest, these nanophotonic things, solid state things like silicon vacancies and whatnot, it's like 100 megahertz to a gigahertz bandwidth. And often, so that corresponds to 10 to the minus 3 nanometer. And often in astronomy, they're talking about a nanometer that they're imaging. It depends, though. I mean, some things you want really high resolution, for example, for a dynamic process like rotation of stars and these kind of things. Also, for very high spatial resolution, there's a intimate link between how much you're averaging over in frequency and how good a spatial resolution you have. So there are actually also limitations to classical techniques for spectral noise removal, because that's also relies on you integrating over different frequencies. So I'm not saying that there are use cases of these narrowband where you don't need it, but otherwise you need to think about how do I make my quantum memory more broadband, which you could try and multiplex them together to cover a bigger thing. Then becomes definitely more challenging, right? Because instead of having maybe 100, I need now 10,000 of these. Then we're really not talking about near-term things. So identifying the exact targets where this maybe would work in narrowband is definitely something one should look into. And new algorithms for these things as well. All the other things we can look at. What can we do with quantum processing to get that, extract information more efficiently. Also, I mean, to be fair, this comparison is just that, well, current classical techniques use tomography. I haven't proven that there's not better classical techniques that maybe could get the same. So proving like the fundamental advantage is also something that's a little bit open in these things. All right. That was that. Questions before we move to the final one? Nope. All right. You also meant that's a little bit of a sit back and relax kind of thing. So, final one, which is a bit different. So the three that we covered before were all about improving existing techniques, right? That we had classical techniques, but we can do better maybe with quantum. This final one is more embracing, well, okay, but what if can we do new things that you could not do with classical? So we're not trying to improve something, we're just trying to see, we have a new thing here, we have a new quantum thing, can we sense things that we could not sense classically? New measurements. And we've discussed in the morning, yeah, like this quantum gravity and stuff and whatnot, right? So to me, I'm not at all an expert on quantum gravity. And so keep that in mind when I say that my kind of impression of the field is that pick your model. Basically, there are a lot of different models of quantum gravity. They can all lead to some results, and a big kind of, it means my impression is, it might be wrong, is that you need to kind of come up with ways to test these models to actually see if there is something to them or not, right? So there might be a lot of work in designing tests to start to rule out some of these models and whatnot. But yeah, I don't know too much about that. What also you can take is say, well, okay, forget about quantum gravity, just take the things that we kind of believe are there, like general relativity, no quantum, just classical, and quantum mechanics. Now, merging those two together, you can say, what happens when we put quantum mechanics on curved spacetime? So curved spacetime from general relativity, and quantum mechanics, naturally not something to do. So now I'm not trying to probe quantum gravity, I'm just trying to say, can I probe what happens with quantum systems when they start to be at length scales where they're not, at the same point in the computational space, but on a curved space-time. And there are some phenomena like Hawking radiation that comes from that, for example. That is just quantum mechanics and general relativity. It's not quantum gravity. Are there some other things we can do? Are there some tests of quantum mechanics on curved space-time we can do? And some of the candidates is that you can make a quantum superposition between two locations and interfere them. So this has been around for a time. Basically, what you're using is the fact that if I take and make a superposition between a clock being in one location and a clock being in another location, I can start those clocks will evolve according to their proper time in those two locations. And we know from general relativity, there's time dilation, depending on where you are in the gravitational field. So now I can then take that superposition of a clock and interfere it. So word of caution there, if you just take two clocks and put one clock in one location and take a physical clock and put it in another location, that's not a test of quantum mechanics. That's just, I have a clock here, that ticks, and there's a clock here, and that ticks, and I compare them. So that's not a test of quantum mechanics on curved spacetime. That's just a test of time dilation on classical limits, right? And that has been done, naturally, right? We use it for TPS. You need to keep these things in mind when you do it. So that's fine, but it's not really testing any kind of quantum things. You really need to make a superposition of a quantum clock. And people suggested, well, you could do that with matter wave interferometry. Take like matter waves, split them up, put them to two different locations, interfere them, and yes, that would be a proper test of quantum mechanics on curved spacetime. The issue with that is it's super difficult to have large separation with matter wave interferometers, right? We're talking centimeter scale, something like that. That's what you can do. So forget about curved spacetime, because at that limit, it's really just like homogeneous kind of thing, right? Like in high school where you calculate the potential energy, it's G time H, that's what you get your potential energy, because it's a gravitational constant. It doesn't depend really on your curvature at that point. So if you really want to have large separations, it seems difficult to do that with matter wave interferometry. But what you're trying to see is you're basically trying to have the superposition and have this clock interfere, and because the time is different, you'll see the oscillations or the visibility of these drop as they become basically distinguishable states and come back up as a function of time. That's kind of the signal you're looking for, that, okay, this clock interference will change as time propagates. Okay, but I also that, okay, you need large separation, you need a fast ticking clock as well, because basically the signal you're looking at is a phase accumulated over time. The bigger the energy difference between the two clock states, right, a clock is just two energy states that accumulate a relative phase, the big energy, the bigger phase, the faster the phase will accumulate. So you want a fast clicking clock to see it, because it's a small effect in regard to imitation. That's a problem. How can you get large separation? You could use a quantum network. So basically, what you can do is, what is a clock? Well, a clock is actually just two energy states. That's a clock. Then I accumulate this phase. Now, can I make a superposition of clock? Yes, you can. If you take 2 3-level systems, for example, which is just one example of it, so you have a ground state G, another ground state C, and a third ground state C2, C1 and C2. C1 and C2 is what I'm going to identify as my clock state. G is just my no clock state. Right, so I'm saying that's just my background. And now I can make an entangled state where basically I have an entanglement between either one system is in G and the other one is C, C1, vice versa. And then I can start my clocks by now applying a local rotation, so I come into a superposition between C1 and C2. So what is this? Then it's just basically a superposition of one clock being in one direction or the other one. So here I actually have my matter system locally there, but I'm still making a non-local superposition of a clock between this. And that's how you can use a quantum network, right? Because I use a quantum network to entangle these guys. And that way, use the things that we do for entanglement distribution, photomediated and whatnot, to make that over long distances. I also need to interfere these clocks. And that's where you can use, like in the telescope, also entanglement to do these non-local measurements to do it. So now you can also measure and interfere these clocks through the quantum networks. And this is something that you can expand. So instead of just doing 2 clocks, you can do 3 clocks. You can start to probe indeed, not just time dilation, but also time dilation in curved space-time. You'll start to test, does Born's rule apply also when you have curved space-time? I mean, we expect it to, right? So it's not like we're trying to probe new things. We're trying to probe existing theories that have not been probed in this regime before. So, I mean, we expect them to hold, but maybe they don't. I mean, interesting if they don't, then there's something going on in that line scale, right? I think the example here is that this is a different type of network sensing where we're not trying to improve classical things. We're trying to design new measurements that you just cannot do classically, probing the interplay between quantum mechanics and general relativity. Calls the challenges, like you need good coherence times, right? You need optical clock transitions, especially to probe curvature. Coherence times, you need something like seconds, tens of seconds to something like that. That's where we need to be. And of course, you also need to have good quantum networks. You're trying to see, for example, these visibility go down and come back up. Any imperfections will lower your visibility, as we all know, right? So at some point, if you can't see it anymore, then yeah, you just won't be able to probe it. And often, I mean, where you end up in quantum length scale is you kind of need entanglement distribution on the kilometer scale, horizontally from Earth, right? So you need maybe something that's 1 kilometer below ground, something on surface 1 kilometer above, or something like that to start to probe these things. You can also do with satellites if you want to do something else, but it's not necessary to do. All right. Questions? Okay. Oh, sorry. Yeah. Yeah, good question. I think that the first test you can do is forget about the curvature, but just actually seeing the gravitational time dilation in somewhat of a homogeneous field. There, you would need like a 10-meter difference and something like optical clock transitions, coherence time about 10 seconds. I could see that happen if someone were to pour money into it and do it. Sure, with, I don't know, 5 years, whatever. The larger ones, I don't think we need a lot of technological improvements to do it. But it is not something I mean, especially coherence time and whatnot, it's probably not what you have today, so it does need to be improved. Yeah, it's always difficult to predict the future, but I think it's not something where we're talking 30 years out in the future, right? I mean, it's not something that requires a full-tone computer or anything like that. It's something that, in principle, is relatively simple techniques you need to do. I think that's the best answer I can give you. Sorry. Yeah. Okay. At the end here, so we're going to end a little early, but I think you've had enough at this point. Some things to wander off with is, I think one thing we discussed today is, when you talk about application content networking, what are actually the real applications, right? Keep these things in mind. Is the gain worth it? Are we really in a situation where this is something that's going to change the world, or is it like the doesn't matter kind of thing? Think about it outside of, for example, distribution, kind of what we also discussed here, right? I mean, it might not be long-distance entanglement distribution. It might be, maybe it's just like the spin-field interface that maps into quantum computer or whatever. That goes to, often when people talk about quantum networking, I'm not saying everybody, but they say, oh, quantum repeaters, right? That's what you need for quantum networking. And yes, for long-scale things, you might need it indeed, but there seem to be quite a few things that doesn't require a repeater, which is nice because a repeater is damn hard to make. I personally think like these fundamental tests of nature is kind of interesting. I mean, then we're no longer competing with classical, we're just asking like, what are the new things we can probe with these things? And so on and so on. So, a lot of good questions. I hope that this last thing left you not discouraged, but more curious. And yeah, thanks so much for participating. It's been great. So that's it. Thank you. $30 or something like that, the bus or well.
Yeah, that's correct. So at 1:30, the first group will leave, and those leaving with the first bus, then please take the lunch box with you and main campus. So I would like to thank the speaker again for the 4 nice lectures.
Thanks. Thank you.